How do you translate that into a hardware architecture? What's shown on top is basically what the hardware architecture looks like. Okay. So what we can see over here is, so what we can see over here is that, let's take a look at operation number 2 for example, right. So operation number 2 is an addition, right. It occurs at time 1, phase 1 of the clock. So that means that I should basically be interested in what are the inputs coming to the adder at phase 1, okay. I can see that this is one of them and this is the other one, okay. So where are they coming from? This one is basically coming from the adder output over here, and this is coming from the adder output over here, right. So what does that correspond to? If I go back and look at operation number 2, it had two input edges, one from 1 to 2, the other was from 4 to 2. So df from 1 to 2 had a df value of 1, and from 4 to 2 had a value of 0, okay. So when I say that the df from 4 to 2 has a value of 0, essentially what I am saying is the input to 2 which is coming from 4 is to be taken from the output of my adder module with 0 additional registers after it, okay. That is what this corresponds to, this line out here. Okay, this is the output of the adder, is output of adder with 1 register delay, right. So in other words, this corresponds to the edge from 4 to 2 and this corresponds to the edge from 1 to 2. Let's take another one of the example edges over here. Operation number 4, okay. Operation number 4 is getting both its inputs from multipliers, okay. In other words, the inputs to operation number 4 are coming from operation number 6 and from 8. Yes, but what I am saying is, you remember what I said, this is just a data flow graph. When I say that it is getting its inputs from multipliers, what I mean is the functional unit from 8 to 4. Oh yes, I am sorry, thank you for pointing that out. That's because I missed a register over here, right. So yes, that is an important point. There is a register out here, okay. Without that, the df would have been negative and there would definitely be a problem, okay. Thanks for pointing that out. So yes, the inputs to 4 are coming from 6 and from 8, okay. The corresponding df values, let's just simplify matters and go look at this. These are the two values that I am interested in, right. Df from 6 to 4 essentially corresponds to 0 minus 2 minus 2, so minus 4 plus the 1 sample delay over here, right. So it basically becomes 4 minus 4 equal to 0, okay. And on the other one, it basically becomes, this would start at time 1, end at time 3, plus 1 sample delay, so time 7 minus the time when this is scheduled. This would be required. So basically this would be requiring the data at time 0 plus 1 delay over here, so that is at time 4, minus 1 which is the time when this is scheduled, minus 2 which is the pipeline latency of the multiplier, right. So if I work through this, what I will find is that the df for 8 to 4 comes out to be equal to 1 and from 6 to 4 works out to be equal to 0. So in terms of the hardware, what does that mean? It means that At what time instant was 4 scheduled? At time 0. So let's go look at the inputs to the adder at time 0. This is one, this is the other. Okay. Where do those edges come from? This one basically comes with one extra register out here from the output of the multiplier, whereas this one comes directly from the output of the multiplier. Okay. So this, in other words, corresponds to the edge from to 4 with df equal to 0, whereas this other one corresponds to the edge from 8 to 4 with df equal to 1. This is what I am seeing over here. Okay. So the bottom line is this: once I have shown you this architecture, you can then interpret it backwards in terms of the original design. But if you think about it, it is also not very hard to come up with this architecture, because once I have come up with all these df values, what is the procedure that I should follow? First put down these two blocks, one adder, one multiplier. Okay. Then put down the different phases 0, 1, 2, 3 for each of the inputs. Okay. At phase 0, what is the operation that's being executed on the adder? Find out where its inputs are coming from. Find out what are the df values on those links. Put an appropriate number of registers to delay those links and then connect them up to the appropriate phase. Okay. It turns out that in this case, the output of the adder, you might have to have up to 5 delay elements on it. That is because the maximum value of df essentially corresponds to this value, 5. That's why I have 5 delays out here. Okay. And if I look at it, the df values that are coming out from the multipliers, the max is basically 1, which is why I just have this 1 over here in one particular instance, or rather for 2 instances, for 0 and 2, time instance 0 and 2. Okay. So this should tell you that the procedure that you can follow in order to get a folded architecture is fairly straightforward, right? You start off with your data flow graph, you determine the different folding schedules at which time instance those different operations need to be scheduled. Is that a very trivial thing to do? Not exactly. That's exactly where we are going next. Okay, that's what we are going to be looking at after this, but it can be done. So assuming that I can come up with those folding orders, the next question is, how do I compute the df values and how do I come up with the hardware architecture? That is more routine, fairly straightforward to do, right? I can basically put down a basic architecture, put down the number of registers after it and make all the connections. Okay. If you think carefully about it, there are still a couple of tricks involved over here that are not very obvious, right? For example, if you look at this particular delay element, right, this register out here, it is basically the output of the multiplier being put through one register and then being provided as input to the adder at phase 0 as well as at phase 2, right. Now the fact that I could use that particular register in order to do both of those was not entirely obvious from the original design, okay, that I could share this particular register. In particular, if I had chosen to give this multiplier input to the other input of the adder at phase 2, right, I won't be able to share this register. I would have ended up needing 2 registers, or I would have had to do something else to my diagram over here. My diagram would have changed in some way. I might not have been able to share some of the wires at least. Okay. So there are some finer details that are involved over there that could further, result in minor modifications to your design, but not very significant ones. They would mostly be relatively small changes to the design that you end up with. Okay. So to summarize, once I am able to come up with a set of folding orders, a folding schedule, the process of converting that into a hardware architecture is something that is reasonably automatable. When I say automatable, I can write a program to automatically create this structure once I give you the folding orders. Because what does that involve? It basically involves computing all the DF values and then making all the connections. That is something that computers are very good at, because there is a fixed procedure for doing it. You can write a program to do it and you can automate it, right? And that is one of the key takeaways from pretty much everything that we are trying to do in this course. What are the processes over here that can be automated, right? And if they can be automated, how well do they work? Okay. So the next thing, of course, that you need to keep in mind over here is, if it can be automated, why are you learning this? Right? After all, there is a compiler or a program that can do it for you. That's exactly the point of this course. You need to understand how the compilers work or how the programs work, so that you understand where the problems are and what it is that they are doing, so that if and when they don't give you the best possible design, you understand why and you can actually work around those.